I don't know if you have heard that, but this meeting is being recorded. We're also putting this session on our YouTube channel, and we will be sharing the stuff and everything through our social media accounts. So you're very welcome to ask questions and follow up after the session with questions or doubts. And anyway, no more spoilers. I'll explain everything in a minute. One more minute or so, and we'll kick off.
We cannot even add information to the Meetup page, isn't it?
No, it's completely down. So normally you can send emails to attendees to send like information prior to the event and whatnot, but we cannot even log in or access anything. This is a shame because we had about 140 people. There was a lot of people who RSVP'd, and I guess a lot of people cannot find the link anymore. It was supposed to be on the email, but of course that's what happens if you lose the email and all that.
And the point is that, did we send an email to everybody?
Yeah, Meetup sends an automatic email when you RSVP to the event, but then that email can go to spam, or maybe you submitted your attendance a couple of weeks ago or 3 weeks ago, and then you don't have that email anymore. Yeah. So it might be lost in the wind. In any case, we will put this video on YouTube, and if people have interest on going deeper and learning more, we can even try to find or to create a follow-up workshop, even more advanced. Maybe your brain will hurt a little bit from today's session, although the presenters are going to do it nice. But hopefully you did the last week's workshop that Carmen did last week on the introduction to Qiskit, and that should give you, at least the ones who are not that versed in quantum computing, that should give you the introduction to what we're going to be talking about today. All right, so without further ado, we are in 1607. As I've mentioned, unfortunately, meetup.com decided to go down right in this moment, about 30 minutes before the event. So unfortunately, a lot of people who wanted to attend will not be able to find the link. For those who are in, thank you very much for coming, and thank you for attending the third event of Quantum Barcelona. So we the organizers, the panelists that are today with me are very happy to have you with us today. Of course, this is the COVID way of doing events. The spirit of this community is building a group of technologists and business people and all those who are interested in quantum computing in Barcelona. And hopefully we can very soon do a proper face-to-face quantum beers. Now, in the meantime, we will have to do it online. The good news is that we can welcome some of you who are not from Barcelona and can connect and join us from many other places around the world. But hopefully, and if all this news about the vaccines works as expected, maybe during the Q1 or perhaps Q2 of next year, we can see each other and we can see our faces and drink beer together. So again, third event. We started the first one a couple of months ago where we did this little game on quantum beers and we created a circuit together and then decided together what were the topics that we were going to talk about. And we took all that feedback from you guys on creating the agenda of what the next few months are going to look like. And at the end of the event, I will invite you to what's coming in January and February. No spoilers. So I want you to stay until the very end. And invite you for all the next workshops and talks that we're going to be organizing still online for the time being. Then this is one workshop that was divided into. Last week, Carmen, who's here with us, gave some of you a really nice and an amazing introduction to Qiskit, which is the perfect first dive into quantum computing with Python and your notebooks and the different options. And now today we're going to go a bit deeper. Some of you actually asked for this and you specifically requested to go hard at the beginning and go straight to the bone of what quantum computing can do. So in order to do that, today we have an amazing team of panelists who are going to talk about quantum machine learning. So we have Dr. Muñoz-Gil, Gorka Muñoz-Gil from ICFO. We have Dr. Alex Dauphin from ICFO as well. And we have Adrián Pérez, who will be showing us some of the things they've been researching over the last few years and what's the state of the art in quantum machine learning, how these two worlds join together. And then I will be trying to handle the Q&A. Some of the questions we will tackle them at the end or between each of the talks, but we will have plenty of time to go over that. So without further ado, I hope you will all enjoy this session. And Gorka, all yours.
Okay, thank you very much, Sergio, for this kind introduction. So let me share the screen. Okay, good. So let's confirm that you can see the slides. Okay, so welcome everybody. Already Sergio did a really nice introduction. So the topic of today will be, as I said, quantum machine learning. And indeed, we live in a very nice period of science and technology because we have two highly rising topics. From one side, we have quantum computing, and from the other side, we have machine learning. And we have the opportunity, myself and the other two panelists, to work in between these two incredible, interesting topics. So the plan for today, as Sergio did, will be quite technical, but we will try to make our best to make it understandable. And also, we'll be very happy to answer any questions you may have. We will try to either make it in between the different points of the outline or either at the end of the talk. So, okay, this works nice. So what's the outline? So we wanted to start by putting everyone on the same page, and Adrián will introduce classical machine learning very fast because we expect that many of you already know, probably many of you may know better classical machine learning than we do. Then we'll talk about special purpose quantum machines, so some kind of quantum machines, not quantum computers, but something more specific that we can build to enhance machine learning algorithms or to create our first prototypical quantum machine learning architectures. Then we will deep in on fully quantum machine learning, and there we will talk about how to implement all these machine learning algorithms in quantum circuits. And at last, we will have Alexandre talking about his last paper on how to train and how the loss function looks in all these quantum variational circuits. So without further ado, let's get Adrian to talk us about classical machine learning. Please, Adrian.
Yeah, thanks for the introduction, Gorka. Will you be passing the slides for me?
Probably you can just have it.
Okay,
yes.
Thanks. Okay, so can you? I assume that you can see that.
Yes.
Okay. So just to be sure that we are on the same page, I'm going to talk a little bit about what classical machine learning is and how how I consider that we should treat it. For those who don't know, that I assume that are not many of you. Classical machine learning, or machine learning in general, is a state-of-the-art technique for computation. Okay, for computers, and this kind of this field is ubiquitously used for all kinds of problems. So just to make a summary, what we do with quantum with machine learning is developing an algorithm, and give to the algorithm some data in such a way that this algorithm learns the features of the data, the hidden features of it, by some training processing. After that, this algorithm is tested against some unseen test data in order to accomplish a task. Okay, so now after this very brief introduction, I would like to get a little bit deeper on that. The point is that you have to, the main pieces of machine learning are a collection of data that can come from wherever, and an algorithm that can be God-given or can be created by someone. And the algorithm learns the subjacent hidden features of the data set. It is very useful in the case where we as humans do not have enough knowledge to know how the data set is structured in deeper layers. So this algorithm from machine learning can do it automatically. So it is very, very efficient. This process must be taken is driven by some cost function that measures how well the task is accomplished for the training data, and then that must be generalized for an unseen data set. And this is very important because in the case that our algorithms only can learn very well the training data, but that cannot generalize to some other data, then the algorithm is not learning; it's mimicking. Okay, now in order to set a little bit the level that we are about to talk here, the key idea of machine learning is embed any problem into this kind of fashion. That is, we must find a mathematical function that derives from the space of data set, the x variables of the data set, to the space of solutions in this data set, and we have to find the best possible function that learns the data. This process is driven by some cost function, chi-squared, okay, that must be designed in a very precise way in order to achieve that the algorithm does whatever we want to do. And the solution to this problem in general is just the solution that minimizes this chi-squared. I would like to make a note here. Machine learning, from my point of view, is not equal to artificial intelligence, because there is a need of a human brain behind the algorithms to actually get what we want to do. Okay, and I will illustrate that with an example. I don't know if you know this picture. It's kind of famous. The problem to solve here is the following: we are in the Second World War, and we receive some planes with some bad impact on it. Okay. And if we were at the 21st century, we would give this data to a machine learning algorithm and say, okay, where should we reinforce the plane in order to obtain more plane, to not lose any of them. And the algorithm will give us the solution. Okay, you must reinforce the plane in the zones that are impacted by the valids. Okay, the answer to this problem is actually to reinforce all zones that are not impacted by the valids, because in this case, one impact in that zones is equal to a lost plane. So what I want to illustrate here is that we cannot let the machines to do all the work, and there are still some things that we have to take care about in order to get progress into this field. Now I will give some review on classes of machine learning in order to not underestimate what we have achieved. Okay, there are mainly 4 classes of machine learning. First one is supervised learning, and it consists in taking a data set that is conformed by some X data and some labels, and the algorithm must know how to distinguish between some labels. The same can be applied for unsupervised learning, and in that case, the main difficulty of this problem is that we don't have any label, so the algorithm has to learn it by itself. This is done in many places. For instance, the Netflix performs some machine learning in order to recommend us the next series or the next film to watch. The third part that I would like to say is generally algorithms that consist on creating things by learning from some previously seen data. For instance, this photo here is not a photo. This person does not exist. You can see this person does not exist.com in order to see how well generative algorithms perform for human faces. The fourth one I would like to mention is reinforcement learning. This is some procedure that makes the machine learn between how to get a reward and how to explore the field in order to get better solutions. This kind of algorithm was able, for instance, to defeat Garry Kasparov, the world chess champion, in some game. Well, there are many things that we can do with machine learning, but there are many things that have to be done in order to apply machine learning, and that is very important. Okay, because nowadays we owe the machine learning to very specific things. For instance, tailor-made hardware such as GPUs, they are very well. They are used very broadly, and there is almost no computers without one of it, and they are kind of mandatory for all machine learning algorithms. We owe machine learning also to specific models and some optimization algorithms that make this kind of procedure very efficient. We owe the machine learning also to software tools that allow us to code in a very fast way, and to some theoretical achievement that date from the late 80s, so almost 30 years ago. And why should I say all these things? It's because we cannot underestimate machine learning. Machine learning is not a field coming out of nothing, and technology itself has changed in order to adapt to the needs of machine learning. Also, so we know that machine learning is a very powerful tool, and we want to use it more and more. But we have to change lots of things in order to get that. I say this because quantum machine learning is in a very early stage, and we cannot do most of the things that classical machine learning does nowadays. But I am pretty confident that in the future we will be able to do that. So now I will just give the word to my friend Gorka, and well, he'll tells us about some specific machine learning structures. If I am able to, okay, thank you.
Okay, great. So let me come back to the Okay, thanks, Adrian, for the nice introduction. So let's start with the quantum machine learning. Okay, so probably many of you have heard about quantum computing and have heard probably because of the workshop that Carmen gave about quantum circuits, quantum computers, etc. But from the beginning, we didn't have these tools. Okay, we didn't have quantum computers. So at the beginning of machine learning and at the beginning of quantum machine learning, researchers were trying to develop precise quantum machines that were not quantum computer in order to do this quantum machine learning task, the same task that Adrian talked about, supervised learning and supervised learning. And before going to the quantum, let me tell you a little bit about the story of a part of the story of machine learning. And indeed, if you take a look at the first papers on machine learning and the first results, you will see that they are closely related to some of the theories we use in statistical physics. Okay, so if you take a look at the first papers from, for example, Hopfield and Gardner, who were like kind of the first to deeply study machine learning, you will see that the theories they use are the same ones we know from statistical physics. And you can see it very well if you take a look at the, okay, so let me put the pointer. You take a look at a neural network as I'm showing here. And okay, you already know that we have some neurons and then we have some connections between the neurons. Okay, so if you take a look at what we call a statistical physics model or a spin model, okay, we have a certain lattice, a grid, in which at each vertex we have, let's say, a particle, an atom, a molecule, or whatever. So in physics, we describe these models by saying that the edges tell us how the interactions between these two bodies are. Okay, so at the end, we have a set of atoms or molecules or whatever interacting between each other in the same form that neurons interact between each other. So by making this analogy, people indeed show that you can study both fields with similar techniques. And indeed, Hinton and Tishby, more recently, have used these kind of techniques, and many other groups study machine learning from this statistical physics direction. And one of the best examples to see this analogy is are the Boltzmann machines. I don't know if you know them. I will review them very rapidly. So basically, in a Boltzmann machine, we have well, I will talk about restricted Boltzmann machine in which you only have two layers. Okay, we have one layer of neurons that we call the visible layer, which has the visible neurons, and then connected with some weights, just as in a normal neural network, we have the hidden neurons. What is the difference between a normal neural network? It's that in normal neural networks, we have a feed-forward scheme. Okay, so we put things in the visible, and then we propagate them through the hidden neurons. In a Boltzmann machine, we have a bidirectional scheme. Okay, so we can go from the visible to the hidden, and from the hidden to the visible. Okay, and there is a precise function that takes us from the visible to the hidden, given these weights. So if you give this to a physicist, they will tell you, okay, let me put spins instead of neurons, and then I understand what I'm looking at. Okay, so at the end, what we have, and the way indeed of going back and forth between the visible and the hidden neurons is very similar to the way these spin models go back and forth. Okay, and now in this case, these weights are, for instance, the interaction between the spins, atoms, or molecules, or whatever body. Okay. So I have to say that everything is classical. I didn't put anything quantum here. Okay, these spins can be classical or it's just physical bodies. So now let's come back to the Boltzmann machine. So what the Boltzmann machine does? So basically, we take a training data set, for instance, all these cats, and we train the machine. And the goal of the training is that after the training, I generate new images, okay? And how do I generate? So basically, I sample, which means that I go back and forth in this, following this precise mathematical expression. And then at the end of this sampling, I get in the visible neurons images similar to the ones I have used to train, okay? If we go deeper into the mathematics, we can see the following, okay? let's come back to the physical model. Okay, so as in any physical model, I can give an energy to each configuration. Okay, so each precise configuration of these neurons or these spins, I can give an energy. Okay, and I choose to define the energy in this way. So the energy of a certain configuration, sigma, so sigma I would be the value of this neuron, sigma I plus 1, the one of this neuron, etc., etc. So basically, the energy of a given configuration is the value of a neuron times the value of another neuron times the weight that connects both neurons. And then I also consider what I call a bias, that is just the value of the neuron multiplied by a number. Okay, so now given this energy that I call energy, but this can be, you can call it as you want, I can use a feature that we know from physics from a long time ago, and it's the Boltzmann probability. Okay, so I will say that the probability that I find a given configuration, let's say a visible configuration, is proportional to the energy with this exponential form. Okay, I won't enter into the details, but I would just wanted to show that, for instance, the smaller the energy, the bigger the probability. Okay, so what's the goal of the training? So in mathematical terms, the goal of the training is to minimize this function. But if we don't enter into the mathematics, the goal of the training is to increase the probability that our model generates an image that is close to the training set. So that the probability that my system creates an image of a cat is very high. Okay, so if the probability is very high, the energy is very small. Okay, so I have to find these low energy configurations. Okay, I have to find, and what I need to do is that in these low energy configurations, I need to put my images of the training set. There is one problem here, is that this back and forth that I call sampling, in order for this sampling to be efficient, I need to fulfill some properties, and indeed these properties are not fulfilled in the Boltzmann machine. So this means that sampling in a Boltzmann machine is very, very hard. Indeed, it's NP complete, which means that it's very difficult. Okay, so basically what we will do now is to take a look at the quantum version of a Boltzmann machine in order to see if we can leverage this problem of the sampling. Okay, and indeed we are going to look at it from 2 points of view. First, I will talk about quantum neurons. Okay, what happens if now all these neurons that I had before are quantum? Okay, and then I will talk about if we can create a quantum system that allow us to train more efficiently the classical network. Okay, so from the first point, from already the 90s and the 80s, there were some papers that were trying to research on this direction. So basically, at the same time that machine learning started to get some attraction, there was some ideas already concerning creating these quantum counterparts. Indeed, my boss, Maciej Lewenstein, already in 1994, published a paper in which he did the quantum counterpart of the most basic unit of machine learning, which is the perceptron. And indeed, just recently, our group has published a paper in the archive. Okay, so for those of you who don't know what this means, basically there is a web page that is called Archive, in which we put our papers so everyone can see them in an open access way. So basically, if you go to this archive or you put directly this to in Google, you will get the PDF of the paper. Okay, and you will see this through all the presentation today. Okay, so coming back to quantum machine learning, we see that there are many examples of people already in the 90s and early 2000s trying to do all this quantum machine learning from a theoretical point of view. What happened? We didn't have the tools to implement all these models. However, now we are close to being there. So there is a new blossom of quantum machine learning models. And indeed, we can see now people trying to create quantum Boltzmann machines, quantum Hopfield neural networks, quantum generative adversarial networks, etc., etc. Okay, so let me come back to the Boltzmann machine and tell you what's a quantum Boltzmann machine. Okay, so for the classical Boltzmann machine, I told you that, okay, I have neurons and I can do the relation between neurons and classical spins. If now I go quantum, I have the same thing, but now the neurons, I will treat them as quantum spins. Okay, and if I introduce the term quantum, I introduce many interesting features as entanglement, superposition, etc. Okay, and also as we are now treating quantum spins instead of classical spins, I need to change my energy function, so my E from before, and now it will be a quantum energy function that we usually call a Hamiltonian. Okay. So thanks to this quantumness, as I said, we have very interesting features. For instance, now instead of having my Boltzmann machine in a given configuration, because it's classical, no? In classical we have either that we have one configuration or we have a different configuration. Now I can have superpositions, for instance. And this can allow me to get more efficient ways of training these machines. Indeed, in these two papers, they explore what happens if we train these kind of Boltzmann machines. Okay, and the first thing they show is that there can be an exponential speed up compared to the classical counterpart in the training of the Boltzmann machine. Basically, because what they claim is that the sampling, all this very hard procedure that I told you that is needed to both training and extract images, now is much more efficient. And also, very surprising to me, they were able to show that a quantum Boltzmann machine here, QBM, was indeed having a better accuracy in the generation of images than the classical version. So for instance, here I'm showing the Kullback-Leibler divergence is just the same loss function that I was showing, is similar to the loss function I was showing you before. So basically, the lower we are, the better. Okay, so you can see that this is some results for very small data sets. The quantum Boltzmann machine reaches lowest values of this loss function, which means that the train is better. Okay, so there is all the open question if this is indeed also happening in bigger data sets and until when we can push these quantum Boltzmann machines. Okay, so now we have what happens when we have quantum neurons. Now let's come back to classical neurons and let's try to use a quantum device in order to improve the training, okay? So, and to do that, I will talk again about sampling, okay? So you will see that everything is about sampling in my part of my talk. So I told you that the loss function was related to the probabilities, and this was related to the energy. Okay, so basically, when we have a trained machine, okay, we have a machine that has been accurately trained, we have that the images of the training set, so the good images, have a very low energy. Okay, if energy is this is high energy, this is low energy. So the best image or the best configuration is in the lowest energy. So how do we do to reach this point? Okay, so to do that, we have to do this sampling, not going back and forth between the visible and the hidden. So in terms of the energy, how does it look, this going back and forth? So we start with a random configuration, okay? We put in the visible configuration a certain, in the visible layer a certain configuration, and we start doing back and forth. So this means moving around the energy landscape, okay? And if we are doing classical sampling, which means that we are going step by step moving the spins, we explore it in this way. Okay. So here you can see something already that it's makes troubles. Okay, that is we have to go up these hills. Okay, so if you now consider the energy and the loss function is the same, this means that here we are going against the gradient of the loss function. Okay, so this means that when we are doing classical sampling, it's really hard to go up to these hills. And what it happens is that we normally get stuck in this what we call local minima, which is a point which is a minima in the region, but it's not the real minimum value. Okay. If we do this with a quantum computer, we can use a very special feature that is quantum tunneling. Okay. And I won't enter into the details, but basically what you can do is to traverse these hills. So you don't need to go upwards, but you can just go from one point to the other. Okay. So if you take advantage of this, you can see that now sampling is much better because we don't need to go against the loss function, and indeed we can traverse directly to the right solution. Okay. So indeed, this can be implemented already, and already in 2015, the people started implemented in kind of quantum device. It's not exact quantum computer that is D-Wave. Okay, and basically what they show is that you can implement some problems in D-Wave Okay, so here you can see two images of D-Wave, and this is what it's really, these are the different qubits that D-Wave has. So basically what they show is that you can implement your Boltzmann machine, for instance, in a quantum, in D-Wave, okay? And then use D-Wave to do this quantum annealing, okay? Doing this quantum sampling, which means doing the sampling using this quantum tunneling, okay? Okay, now you may ask, okay, what happens if my problem is not solving a Boltzmann machine? Is this useful for anything else? Well, indeed, it is, because many problems can be translated to Hamiltonians. Okay, so there is a way that we call Kubo that takes transforms our problem to a Hamiltonian. Okay, this translation is not easy. Indeed, it's NP hard to find the Kubo problem for a given problem, but the Kubo solution for a given problem. But for some problems, for interesting problems, we can find it. For instance, maybe you know about the max cut problem, which is that given a graph, which is the cut that crosses more edges of the two created sets. Okay. So basically, this is an optimization problem that is used in many different fields, and this can be translated into a Hamiltonian. Okay, so this would be the energy function of the Hamiltonian. And now we can use a quantum annealer to do the efficient sampling. And indeed, there are many, many different examples of this working. For instance, people from Volkswagen have used this formulation to optimize the traffic flow, or even other groups have used it for finance, for instance, for predicting final crashes or for solving the optimal trading trajectory. And also this has a lot of implementations in chemistry, for instance, in the conformations of proteins, etc., etc. Now you would ask, okay, I have taken 20 years to get a quantum computer and I don't have a quantum annealer. Can I implement this in a quantum computer? And indeed you can, because there are ways of creating a version of quantum annealing in a quantum circuit that is with the algorithm QAOA. Okay. But in order to learn a little bit more of quantum circuits, I will leave the floor to Adrian.
Okay, thank you very much, Gorka. Well, as you may have already seen, it is pretty obvious that quantum techniques may provide some advantage when dealing with machine learning or some other optimization problems in general. So just to be sure, can you see my image? Okay.
Yes.
Now, after this very interesting and, as a matter of fact, necessary introduction to how quantum computing or how quantum mechanics work, let us move to a field that is just a little bit closer to what machine learning is as we understand it. Okay, and how to use quantum algorithms, quantum circuits, quantum computers for implementing machine learning techniques in this era and in the future. Okay, well, machine learning may have a very precise target when we implement quantum for this kind of problems, and this is the following. We expect that quantum computer is much more efficient than classical computers when dealing with data and with manipulating data. So what we would desire, the most desirable possible consequence of quantum machine learning when we apply quantum computing, would be to obtain exponential advantage in the number of operations in the time that it takes to solve a problem. Why do we do that? Why do we desire this exponential consequence? Well, as many of you may know, if you have some background on quantum computing, at least a little bit of that, the amount of data that can be stored using quantum computers require exponentially less resources than classical computers, and that is due to a quantum mechanical property that is called a Hilbert space that is inherent to the quantum world. That being said, that is not always the case, and there might be cases where you cannot get these exponential advantages. But nevertheless, there might be different quantum features that could make quantum machine learning interesting and useful. And in this minutes, we will review some of them. I would like to highlight now that the most probably the most interesting fact is that quantum computers do not treat data equally to the classical one. And we could find classically intractable algorithms that are very easy to solve in quantum machine learning. For instance, if you know the Shor algorithms, this kind of problem. It takes advantage of a very specific property of quantum mechanics. And last but not least, we could get savings in the energy consumption of the computer, since supercomputer now it's well, really costly in terms of energy, in terms of environmental impact, and quantum computers could reduce the CO2 footprint of computation. Okay, so now I would like to talk about three main topics. First of all is quantum-inspired algorithms that are inherited from quantum mechanics, but can be implemented in classical computers. Then I would like to talk about fully determined algorithms, and that is already circuits and things that can be used in circuit in order to apply machine learning to that. And then we will move to variational quantum circuits. We'll link with our invited talk here. These variational quantum circuits belong to the class of hybrid computation that takes care of quantum and classical resources at the same time. Okay, so let us move now to quantum-inspired algorithms. As I said, quantum-inspired algorithms are those that can be run in a classical computer, but are inherited from techniques to study quantum physics. Okay, and the king of these algorithms is the so-called tensor networks. Tensor networks are a tool to simulate a slightly entangled quantum system, and they have the property that allow to represent in a very compact manner highly complex quantities without by losing as least information as possible. So it's a very efficient and compact way. To cut a long story short, I will not come into details, but those are different models from tensor networks, and tensor networks are consist in the following. Each node that you can see here, or the triangles, so those are tensors that have as many indices as the number of legs right there, as the number of legs for every node. And every shared edge between two nodes is a sum of our indices. So by using this representation, we can just we can split an information into different places, and when we make them all together and compute some quantity, we recover almost the exact value, but not exactly, but a very accurate approximation. And they are based on mathematical tools such as singular value decomposition. So those are algorithms developed for quantum physics, but runnable on classical computers, and they are very powerful and very useful. And we have already some examples for the use of these tensor networks in many cases. For instance, finance portfolio, or the really well-known MNIST handwritten digits, generative models, high energy physics, most of them. For instance, there are enterprises that already use tensor networks to perform quantum-inspired calculations. The second piece of the quantum-inspired algorithm that I would like to talk about is the classicalized, quote, quantum algorithms. The story is the following. Let us think that we have some classical algorithm that works okay, works kind of well, and then someone develops a new quantum algorithm that is exponentially better than the best known classical one. On a second round of optimization, there is a classical algorithm that works not better than the quantum one, but almost. It's very close. Well, that is something that happened in year 2018 with the work by Ewing Tang. And well, what she did was taking some well-known quantum algorithms and classicalize them in order to make them runnable on classical computers. The key idea is that, well, quantum computing, and quantum mechanics in general makes use of sampling, as Gorka has said several times. Makes use of sampling. And well, this is inherent to the quantum nature of this kind of systems. The question is, what if we let classical computers to behave in the same way? And then, with this idea in mind, what she did was obtaining approximate results with less computation classical resources. I'm not coming into details because those works are pretty dense, but if you want to fight against math, I would recommend to read these works. Okay, that is everything I wanted to say about quantum-inspired algorithms, but we cannot forget that quantum-inspired are classical, and they can be run on classical computers, and thus they are limited by the intrinsic capabilities of classical computation. They are very efficient algorithms, but classical at the end of the day. Now let us move to circuit. Let us move to circuit, and let us talk about fully determined algorithms. Those algorithms are totally defined from the beginning of the circuit until the end of it. And they may provide some exponential advantage in the best case scenario. There are many of these circuits, but as most of the algorithms depend on two main pieces, I will explain both of them. Those pieces are the HHA algorithm, named after the creators, Harrow, Hazemi, and Joyd, and that is a quantum algorithm to solve linear system of equations. The second one is the quantum random access memory, that is kind of analogous to the standard RAM memory, but its purpose is to load quantum states efficiently. Let us first go first. Let us talk about the HHL algorithm. I will not explain it because, well, understanding this algorithm pretty well requires maybe another workshop. But I would like to say that this algorithm serves for knowing the solution to a linear system of equations. That is a task that must be mastered in order to perform a lot of computations. So it does that by inverting this matrix A here. And the main point is that the runtime of this algorithm is logarithmic in the size of the matrix A. You may see here where this kappa is the condition number of the matrix and epsilon is the additive error in the solution. The best case scenario happens when both quantities are run in order polylogarithmically in n, and this HHL algorithm is a key piece for many. Well, it's a subroutine for many other algorithms, and it is a very nice prototype for quantum algorithms. However, this HHL algorithm relies on very serious assumptions. First of all, A must be Hermitian and not only invertible, but well-conditioned. That is, there cannot be almost zero eigenvalues. Those assumptions can be relaxed. But the third condition and fourth condition are pretty, are really important for this algorithm, because A must be sparse in order to be efficiently implemented in the circuit. And the vector B must be also efficiently implementable. If we cannot assure that, then the exponential advantage is completely lost, and then this HHL algorithm does not provide any better than any other classical algorithm. So the HHL algorithm is nice, but it is not the solution to all problems. This algorithm could be kind of solved if we had a quantum random access memory, which is a device analogous to the standard one that supports this operation, where there are n possible different values of E, and it requires only a logarithmic number of operations in order to perform this total operator. QRAMs are obviously exponentially more efficient than the standard RAMs, and they are a critical piece for exponential speedup. Every result, depending on the existence of this QRAM, will lose the exponential advantage if this QRAM is not available. And nowadays, no one knows how to do a QRAM, how to build a QRAM with the knowledge that we have. So just for the record, I will give some references for a machine learning algorithm in this fully determined fashion. We can talk about, well, support vector machine for big data, which applies some known techniques for computing a known solution for vector machines. Quantum principal component analysis, the famous PCA, that develops some HHA-like techniques to implement this specific operation on some quantum versions of the k-means clustering using quantum adiabatic algorithms are what Gorka has previously said, this connection between adiabatic and circuits using the QAOA algorithm. Well, the key feature of this algorithm, just a message for you to take home, is that quantum computers can manipulate data very fast. As a matter of fact, well, in the best of cases, exponentially faster than classical computers because the resources needed are much lower. But this is only possible under very, very serious assumptions that are not always fulfilled. So we must be aware of the fine print of this algorithm in order to know whether this is possible or not. Just to finish this part, I would like to talk to you about the first quantum speedup in quantum machine learning that is already achieved, and this is a very recent work, just a pair of months ago. And well, it does not rely on any assumption, but the problem that they want to solve is a very, very specific one. That is the discrete logarithm problem, which is classically hard and quantumly easy. This is the same kind of problem that can be solved using the short algorithms. Many of you will know. And well, as a matter of just to summarize what the paper does, and that we have to face a problem that is classifying these points into blue points and red points. And what it does is developing a quantum feature map that is specific for this problem and that provides this representation. So after this is done, it is pretty simple how to distinguish between classes. Standard SVM can do it perfectly. So okay, this is very well. This is fine. We can provide a quantum speedup for a given problem, but this problem is very, very well chosen in order to fulfill the requirements for quantum computers. But hey, quantum supremacy by Google was also used the same kind of trick, and almost nobody complained about that. Now, let us move to variational quantum circuits for ending. And I would like to say that quantum variational circuits there are many classes of them. We can treat with quantum data, you can treat with classical data and embed that on a quantum computer, or you can use classical data to embed it and process it in the same step. But there are some features that are common to them. Well, the aim of these variational quantum circuits is to drive some quantum data to a specified output state that depends on the task that we want to accomplish. That is done by adjusting the values of the theta parameters in order to minimize some loss function that drives the problem. If the data is quantum, we can only use obviously quantum machine learning, and that is done in the first circuit. But it is very difficult in general to work with a given quantum data because we cannot extract easily information out of that. And for the case of classical data, it must be translated into quantum to work with it, and this embedding is not always optimal. So it is not it is an open problem how to do that. There are recent work that explore the embeddings and processing steps in a same operation. But overall, even if everything is solved up to now, we need some classical computers to minimize our loss functions. And this minimization is not trivial because there are many problems that are yet to be solved. For instance, background plateaus, that is called for vanishingly gradients. The sampling of data and erratic gradients are also a great problem, since most of the optimization algorithms are gradient based. And there is a lack for specific methods. There is no quantum backpropagation that makes everything easy. So just for the record, some examples. You may say here three examples on variational quantum circuits that provide some results. Every one of, well, it follows a chronological order and a conceptual order, since this one, the second one, improves the first one, and the third one improves the second one. And you may say that there are some problems that have already been solved using purely quantum resources. So just to wrap it up and summarize, I would say that quantum machine learning will probably mean a breakthrough in the field of artificial intelligence, but we are not ready yet for that. There are no well-established methods, although there are some proposals, some quantum-inspired methods that are okay, but are fundamentally limited by its classical nature. Quantum exact circuits that are okay, but cannot be yet implemented, since the technology we have is not enough for doing that. All variational methods that use some quantum algorithms are not that resource demanding in a matter of quantum stuff, but they require some major resources in the classical side. And a message. Well, the future is coming. There is already an example of quantum advantage for machine learning. We have done it. There is a quantum supremacy in the machine learning field. In a problem that suits the requirement for quantum computing, that is true, but there is something that we should take into account, because the future will be for sure quantum. So I won't say anything else, and yet I will let just Alex, Dr. Dufan, talk and tell us lots of interesting things.
Okay, thank you. So I will share my screen now. Let's see if it works. Okay, do you see my screen?
Yes.
Yes. Okay, so good afternoon, everyone, and thank you for the introduction that the other speaker gave before, because it's pretty nice. It simplifies my task. And actually, I will start with an introduction, and you will see there's a kind of overlap in the introduction with what was discussed just before. No? And what I want to present today is a recent work that we did that's called Characterizing the Loss Landscape of Variational Quantum Circuits. And just to present myself, I'm working at ICFO, that is the Institute of Photonic Sciences, that is in Casteldefels. And like the main topic of our work in general is quantum simulators. But in the recent years, we have started also to work on machine learning applied to physics, and somehow the opposite way, that is like how quantum physics, like quantum simulators or quantum computer, can enhance these machine learning tasks. And this is also a bit related to this talk. And the work that I will present today is like freely available on the archive. It's print, it's not yet published. And if you can look at it. Also, the code that we use is accessible on GitHub. And the work has been done in collaboration with Patrick Wimboli, that is also at ICFO, PhD student there. To start with an introduction, and I mean, before there was a huge introduction on this, but this machine learning is really a growing field, and we all know that. But the problem is that it's computationally costly. No? And nowadays, I mean, like breakthroughs that have been done are like also hardware, like the introduction of GPUs, and that allowed really to make deep learning a reality. But a natural question also with the rise of quantum physics is whether these quantum computers and these quantum simulators can enhance this machine learning task. No? And as we've seen before, like the first approaches was like kind of pretty clear that was to replace a completely costly part of the algorithm, such as, for example, the matrix inversion that was discussed just before, by a quantum algorithm that is more efficient. And so, I mean, in the talk before, there were like several reasons. And I mean, there is one more that I think is very important for the devices that we have nowadays. Not only there are like this problem of advantages, but also there is the problem that nowadays, I mean, it's really difficult to do like error correction on these quantum computers. And I mean, you know, also for classical computers, I mean, in classical computer, if you would not have error correction, you would not be able really to perform like a lot of operations or gates to your system. But in the case of quantum system, you have like a similar problem. But nevertheless, one can ask whether these devices that are noisy, that are not error corrected, are they useful for something? And this is what is called the NISQ era. And NISQ is for noisy intermediate scale devices. No? And so, I mean, like Adrian was showing like a lot of examples of them before, but among them, the one that we will focus on today are variational quantum circuits. And variational quantum circuit, this is like an example, but there are many architectures. It's really like let's say for me, it's like a huge unitary matrix that is doing like several kind of tasks that can be like rotation of the qubits, or it can also be like entanglement of the qubits between each other. No? And like and at some point you do some measurement at the end of the circuit, and then you try to optimize the parameters of these rotations of this qubit to arrive to a given task. And this we will see a bit more into it. You know? But already, like with these variational quantum circuits, there are many questions that are appearing. No? So one of the like first question, and that is for the moment like studied like pretty broadly, is a bit like the quantum advantage of these variational quantum circuits, which is, I would say, not so clear, I think, from my side. So most of these applications, especially like data-driven, it's not so clear what is the advantage, for example, with respect to a classical algorithm. No? Another thing that is really studied, like for the moment, is the choice of the architecture of the variational quantum circuit. Why an architecture would be more advantageous than another one? And I think that it is not yet clear, what kind of architecture we should use for which problem. No? And a bit related question is how expressive are these circuits? No? So you have basically to perform a task that is like, for example, to fit a function that is highly nonlinear. What kind of circuit do you need to be able to do like to like reproduce this function? No? And then there is also the question on how to train these circuits, and this I will discuss a bit how you can do gradient descent in this circuit. But already, like when you have a lot of parameters to this circuit, you can have this problem of vanishing gradient, or so-called barren plateau that is appearing. And so, how can we avoid this problem? No? Another question that is a general question in learning is how well these circuits, once trained, generalize. No? So especially if you take, like you train them on data, how well can they generalize, on which kind of problem are they good generalize, on which kind are they bad? And finally, a last question that is one that I like and actually is related to the topic of this talk. So how the loss landscape of this circuit look like, no? Because it's also somehow related to this generalization of this variational quantum circuit. And to answer this, I want to do a very brief review on some basic concept of mathematics, that is like the notion of curvature and the notion of Hessian. So imagine that you consider a function that depends on some parameters, okay? And let's say for the moment that is like going to like from the real space, like an n-dimensional vector to the real space, okay? And for the sake of example, we start with a one-dimensional function. And so here I've plotted like different one-dimensional functions. And what you can ask yourself is, okay, imagine that I'm at the red point here. What is the curvature that is there? So here in this example, you see for this parabola, it's pretty clear that the curvature is positive. It's like this U shape that you have here. In the second one, like the curvature is negative. No? And in the last one, it's pretty flat there. No? So this is what you see here. But now you can really ask yourself, how should I characterize these different points? No? And I mean, the answer is like coming from maths that actually around this point, what you can do is a Taylor expansion that is written here. So you write your function as the value of the function at the point plus the value of the gradient at this point times like the difference of displacement with respect to this point, okay? And then you can also add an extra term that would be like a term that is now proportional to the second derivative, okay? So especially at this point, actually, like we see that in this image, we are like at a minimum of the system, which means that the gradient is like vanishing. So this term is disappearing in my function, no? When I will take the gradient. Nevertheless, the curvature is positive. And this is really like the second derivative of the parabola, okay? In the other case, that is a maximum here. What you're seeing is that you have some kind of similar properties. And finally, in the case where like the landscape is somehow flat, this second derivative will be also vanishing. No? So you see that already by studying the curvature, you can try to characterize, by studying, the derivatives of your function, you can try to characterize locally the landscape of your function, okay? But now we can go to the case of a multidimensional function. So the first thing that you can do is a naive exploration. I mean, you take your function in your n-dimensional space, and you start to vary your parameter in the different axes of your n-dimensional space. And then you see how the landscape look like. But this is maybe not the best approach. And actually what you should do is, if you really want to study the curvature, is to, again, do this Taylor expansion. And then you will have this object that is called the Hessian, that is like the second derivative. I mean, it's the derivative with respect to the parameters of function. No? And actually, the Hessian is a square matrix, and the eigenvalues and the eigenvectors of this Hessian are actually giving information on the curvature around this given point. So basically, it's like really giving you, like, eigenvectors are giving you the direction in which, for example, an eigenvalue, like the curvature would be like positive or negative or flat, okay? And so you see already that to study like such a high dimensional function that you cannot visualize, the Hessian is a pretty useful object, and in particular, the eigenvalue and eigenvector of this object. So because I'm talking today about like this machine learning and quantum machine learning, I will first do a brief recap of neural network and what does it mean to have a look at the loss landscape of a neural network before going to the loss landscape of a variational quantum circuit. And so in a neural network, I mean, you have some data that are like vectors, and you have some labels, okay? And then you can have some deep neural network that is basically like mathematically like an application of matrix multiplication, then nonlinear function. Then you take this like a new result, matrix multiplication, nonlinear function, no? Etc. No? And then this is like your deep neural network from the mathematical viewpoint. Then you can define the loss function as like the prediction by this nonlinear network. Here it's, for example, one example of one loss function minus like the label that is associated to this loss function. No? Then you can take the square of it. No? And then you can do that for all the training sets, and you define your loss function as the sum over all these examples. No? And the goal in the neural network is to minimize this loss function given the training set that you have. No? And so you will like adjust the weight A and B that are the bias to minimize this loss function. No? But one can ask, okay, so once I've trained this neural network, how the loss landscape look like, no? And now you really see like why I introduced this concept of Hessian before, no? Because if you're like in the minimum, which means that you see that your gradient is like disappearing at the end of your training because you are at the minimum, you would be interested to see like how the landscape look like. And a good idea again is to look at the second derivative of this loss function with respect to the weights of your system, no? And so you construct like this maps, okay? And then you can have a look at the eigenvalues of the Hessian. This is something that has been studied in this recent work. This is an empirical work. And they arrived to a result that, at least for me, it was not totally intuitive. So, I mean, for me, when you talk about a minimum, I really think of something that is very steep, like kind of parabola shape in all the directions that would be shaped. This is what I would imagine for a minimum. But actually what you find in the neural network is something different. You find some eigenvalues that are positive and big, which means that you really have this parabola shape in some directions. Then you find also a small amount of eigenvalues that are negative, because you never actually arrive exactly to the minimum during your training, but nevertheless, they are very small, so they are very close to zero. And then you find that most of the eigenvalues are zero. And so if you think about it, like the loss landscape of a network, it would be like some direction where some parabola is steep like this, but most of the direction where you would have a flat landscape. No? So this is something a bit counterintuitive for me. And this flat landscape is, I mean, it's conjecture that this is coming from the over-parameterization of the neural network, because you have many parameters in this neural network. And actually, it is also claimed that this is this flat landscape that allows for better like generalization. Okay. And then let's talk a bit about variational quantum circuit and what kind of loss landscape we will have there. These variational quantum circuit, as I said before, they are like composed on several kind of building blocks. Some of them are like rotation gates. That is really that you take your qubits, that can be 0 or 1, then you apply a rotation on this qubit, no? And that is like a kind of local rotation. And then you have like other operations that are like entangling gate that allow you to create like entanglement between different qubits. And so basically the idea, I mean, the architecture is really dependent on the work, but the idea is that really you have like a system where you have some rotation, entangling gate, rotation, entangling gate, rotation, entangling gate. And then at some point you do some measurement, okay? And so for example, here it's not a driven circuit that I'm showing, but the idea, for example, would be like that you want to maximize the expectation value of your circuit such that, for example, you would like maximize the measurement at this qubit at the end of the circuit. This is like a very simple task, no? So it's maximizing this, which means that the loss function that you have to minimize is 1 minus this task, okay? And the goal of this of the training of these variational quantum circuits is to find a set of this parameter theta, like the angle of the rotation, that would minimize this loss function. And so the first thing that you can say, it's nice. You say, it's nice. I have this, I have a lot of parameters. Then like the first optimization technique that I could use is gradient descent. No? So what about gradient descent? So how should I compute the gradient in this circuit? No? So the naive version, that is the first that we would all think about, is like finite differences. So you take the function that depends on all these parameters theta, you fix all of them except one, you add like some value epsilon, then you do the same operation with minus epsilon, you subtract them, and you divide by 2 epsilon. This is the approximation of the gradient, okay? Then you say if epsilon is very small, then this will converge to the derivative of f with respect to this weight theta. No? But nevertheless, you can already see the problem here. So in a quantum computer, what I do to define my loss function, that I'm doing a measurement at the end. But these measurements are noisy. I mean, it's not something that is always the same value. So you will have like some noise that is coming from measurement, are dividing by a very small number that is this epsilon. And the problem in this case is that it makes that the measurement of the gradient becomes not reliable. So it's not a good idea to do that on a quantum computer. But nevertheless, because these quantum circuits are based on unitary gates, and in particular, in the circuit that I was showing, it's like really based on this kind of local rotations of the qubits, you can use another method that was introduced in these two papers that is called the parameter shift rule. And here the idea is that you can show actually analytically that the derivative for such kind of circuit with respect to an angle theta can be written as the difference of something that is now like kind of microscopic. So this S here is really pi half. So it's not something that is microscopic. And to flavor how you can show that actually, as I said before, like this rotation are kind of related to the Pauli matrices. And so you can actually show that that by writing, you could really show like explicitly that this formula is valid for example, for like a single rotation. No? This is what you could show analytically. But what they did here is that they show like more general objects that are like kind of general unitaries. And then you can ask yourself, okay, but how can I compute the Hessian? Because this is the thing that I'm interested in today, you know? And to compute the Hessian, actually, you can apply like twice like this this gradient, which means that you apply twice like the parameter shift rule. And this is like one way that you would be able to compute the Hessian. I just want to mention that, I mean, this is more technical point, but that when you want to like the Hessian of the loss, it's not only the Hessian of the circuit, but it's of the loss. So you have like terms also that are coming from the chain rule. So finally, and this is also something that Rian was mentioning, this is pretty nice because you can implement it on the circuit, which means that you have to do 2 measurements already and then average them, but you have to do that for all the parameters of the system, for all the parameters of your circuit. No? And this means that it scales badly. And I mean, one of the things that is missing now in this variational quantum circuit, kind of an equivalent of what you would have with this like backpropagation that would allow to update all the weights like with like the same measurement. And this is something that nowadays is not present in the circuit. So when you have to compute the gradient or the Hessian, it's like pretty costly because you have to do it for each parameter. And for each parameter, a number of times you have to perform the measurement. So to finish this talk, I want to discuss a bit about the loss landscape of variational quantum circuit now trained with data. And the data set that we consider is like a pretty simple one. That is like that the data like that are two-dimensional. The data that are two-dimensional here, that are the set of points, when they are inside the circle that you see here, they are like class 1. When they're outside of this circle, they are like class 0. And the scheme that we are using is called the data reuploading scheme that was introduced in this paper. It's actually based on the idea that you encode your data in rotation. So a rotation here of a qubit is depending on 3 parameters, but you see our data here are like 2-dimensional. So what you do is that you encode like in this rotation, you encode x1, x2, and then the third component, you put it to 0. And so you encode it in a qubit, then you put like some weights that you have to adjust, like a rotation that depends on weights that you have to adjust. Then you put like some entangling gates, again, some rotation that depends on the data, then some rotation that can be learned by the system, entangling gates, etc. And at some point, you perform a measurement. And this is the way you are defining like kind of your loss. Oh, sorry again. So you're defining your loss. No? So like the measurement that you are here, it's like in the Z basis. So it can be like 1 or -1, okay? And like 1 is associated to the label inside and -1 is associated to the label like outside. And So one of the nice things of these circuits is that they are pretty expressive, so they allow to like to describe like, functions that are like somehow like non-linear here. And I mean, like a nice way to understand why they are like so expressive. You can look at the original paper. You can also look at this recent paper where like one where they show that actually these variational quantum circuits are like kind of analog of like Fourier transform. So this explains that the more time you are like doing this re-uploading, the more kind of the more frequencies you can have, and so you can have more and more expressive in your circuit. Okay? And so the loss function, as I said, is that you compute like the expectation value in the Z basis. That is really like this measurement that we are seeing, and you remove with respect to the level, to the square, and then you do for all the training examples that you have, and this is your loss function. Okay, and then you can have a look at the loss function like before training. You know? This is like the two parameters of your here are like the two values of the data set, like x1 and x2, no? And this is a heat map of the value of the loss function before the the training, no? But you see that the landscape is pretty bumpy here. And when you compute the Hessian that you can do like by applying twice parameter shift rule, what you see is something like this. You have values that are positive, some values that are zero, and some values that are negative. No? And so this means that you are not in a kind of point that will be stable. This is a saddle point because you have many like negative eigenvalues, which means that when you will compute the gradient, you will like, and after the training, the situation is pretty different. So what you are seeing here is a prediction map. And you see that now we can like recover a region that is kind of the inner circle and a region that is like somehow describing the outer circle. And when you look at the eigenvalue of the Hessian, you have like eigenvalues that are positive and most of the eigenvalues that are zero. So there are similarities with the case of the network. Nevertheless, like the main difference is that in this case, like the way you are going from the zero eigenvalues to the positive one is much smoother than what you're observing in the like neural network. And this is, I mean, sort of a question why it is. Like one of the ideas that we see also is that in the decision map, somehow you see that like the boundaries are not so sharp as you would have, for example, in the case of a neural network. And it might be that this is like dependent again on the, so it might be like a feature of this variational quantum circuit, or it might be that this is also like depending on the architecture that you're using. And with that, I would like to go to a conclusion and the outlook of this talk. So I discussed a method like to compute this Hessian in this variational quantum circuit. And so this Hessian is like giving like information of the local curvature, and you can use that during the training or at the end of the training to try to understand what is happening in your landscape. Something that I didn't discuss, but we also discussed in the paper, that you can also characterize like the region of vanishing gradient with this and look that actually are regions that are really, really flat. So it's not only about saddle points, but it's really like flat regions in this barren plateau. Then I discussed a bit like the comparison with classical neural network with some similarities and differences. And I mean, in the outlook, I mean, it would be really interesting to do this analysis for different circuit architecture and maybe try to understand the role of the over-parametrization in this variational quantum circuit and relate that to this kind of Hessian analysis, and a bit the same with the entanglement. So how important is in the entanglement in this variational quantum circuit? And with that, I hope that I didn't bore you, and I would like to thank you for your attention.
All right. So that was it, wasn't it? Is there? I mean, it was intense, I have to say, at least for the ones like me who are not in physics or mathematics. But you guys gave a super good overall vision of all the research that's going around, and the options and the outstanding questions and the outstanding research that we still have to do. At the end of the day, if we were to pick two great buzzwords in the universe today. Quantum and machine learning really score high. But seeing the work that you guys are doing and on making it real and usable really puts our our hopes really high. And also the reason that we're all here, right, to try to see what are the advantages that we can eventually realize with these tools. Just one note, we know what actually is happening with the internet right now. So apparently there's a massive AWS outage all around the world. So it's not only meetup.com, but many sites all around the internet are down. So maybe yet another reason to also do some research on a quantum internet and something like that. Maybe that's a topic for another day. In the meantime, is there any question or any feedback from the public? I don't have any questions here, but please. Oh yeah, that question. Absolutely yes. We're gonna get the talk has been recorded, and we will have it on YouTube for sure. And we will also publish the links and everything on the Meetup group and on our Twitter accounts. I don't know, Adrian, Gorka, Alex, if you want to say anything or to mention anything else for closing.
Well, I would like to say that in case that any one of the attendees here have some question about what we have talked about today, or about whatever that is related to quantum or machine learning that we can now anything about, I would be glad to answer any question, any comment, any thought about that. Well, in case you have, all comments are welcome.
Awesome, thank you, Dan. All right, so just before closing, as I've mentioned at the beginning of the talk, we already have arranged a big part of the calendar for the talks next year. As I said, they will be mainly online.
There are a couple of questions. I don't know if we want to answer them before the closeout. Or...
Oh, you're right. I just saw them as they popped up. You're right. So one question is, what is the best way to get started hands-on? Penny Lane from Xanadu.
I think there are many. I mean, I don't know the opinion of Alex and Adrian, but I guess there are so many options now, and so very nice tutorials on Qiskit, on Penny Lane, on Circuit from Miguel. I don't know. You can choose your preferred one. I don't have a.
I mean, it depends really what you want to do, So I think it depends if you want to play with quantum computer or really this quantum machine learning. For quantum machine learning, I would say Penny is pretty nice because it's like kind of device independent in the sense that you can write your code and then you can like choose on which device you run it. There is also now recently this TensorFlow Quantum that you can use also to do kind of machine learning. So I mean, these are two options. And both of them are kind of documented. But these things are changing very fast. I would say it's a bit the same problem as you have with PyTorch and TensorFlow, normal ones. So I mean, like there are many versions, so the tutorials are sometimes not so up to date. So yeah, I would say for Penny Lane, I think the tutorials are nice, so updated.
Yeah, I would say that in the case of Penny Lane, the main feature of it is that the research group of Xanadu with Maria Schult and all that people is very concerned about how to compute numerical gradients on quantum computers, and that is pretty useful because it is implemented in the Penny Lane framework. So, well, Penny Lane is pretty nice for many things, but in case of gradients, I think it could be the top one. Yeah, because it has an automatic differentiation and everything is pretty well integrated into the overall code of the program.
Let me move to the next question. I don't know why I got all of them just appearing at once. Are there QML apply or applications on knowledge graphs?
So I don't exactly know if knowledge graph is the same as a graph network. Probably yes. If so, there is a recent paper on quantum graph networks. I can try to take a look at the reference. Can I answer in the chat maybe? If you take a look at this paper, it's quite mathematical, but they give a lot of examples.
I don't know if the question is related to the current use that we have on knowledge graphs. If so, some of the things that you guys mentioned on MaxCAD or any traveler salesman problem that uses a graph with nodes, edges, and didactic graphs or otherwise are at the end of the day, if I'm not mistaken, the bread and butter problems for this QML, right?
Yeah, so yeah, but this would be like applying quantum algorithms for classical problems, no?
Yeah.
In that case, I don't know if there is a quantum algorithm for classical graph networks, but there are implementation on quantum.
There is, no? Okay. Sometimes it's platform specific. So for example, if you use this Gaussian boson sampling, you can like somehow sample your let's say quantum computer or quantum simulator to have information on some graphs. So you can compute, for example, like the Hafnian of a graph or some kind of quantities like this. No? And then from that, you can maybe learn something from your graph. This is one of the hopes. So for example, Xanadu is working on that, no? Try to understand how like their device and this Gaussian boson sampling would help in some tasks that can be also classically involved. So
yeah, Gorka just has put on the chat the link to the paper that discussed that. On a completely different topic, could Gorka explain the connection between classical spin and quantum spin?
Yes. So I mean, taking it to the basics, instead of talking about spins, let me talk about bits, no? Because a spin at the end, you can think of a property of the atom that it either points up or down. Okay, so if we go to bits, it's either 1 or 0. So it's the same difference between a bit and a quantum bit. No? A bit can either be 0 or 1, and a quantum bit can be in a superposition between zeros or ones. No? So then you can have access to many other properties if you merge many qubits. So with the spins, it's the same. They have the property that they can be in a superposition between up or down.
Awesome. And the last question that I have for now, and really interesting one, I think. What do you guys think? And I think it would be interesting to hear the opinion of the three of you. What would you say is the main bottleneck at the moment? Is it the number of qubits, error correction, lack of algorithms, maybe a combination of all?
Well, I'll be brave enough to answer this question. I have the opinion that the main bottleneck now is the lack of algorithms, and I will explain why. Well, up to now we couldn't be thinking about that the problem for quantum computing is that we have a few qubits, a little number of qubits, and there were a lot well, they have errors and they were very difficult to correct. Okay, so we can do two things. The first of all is improving the quality of the computers, more qubits, better qubits, error correction, whatever. And then we could apply the algorithms. But in order to develop these algorithms, we need to know more things about what is happening in a quantum circuit, and we don't know yet what is happening there. There are many things that are unclear, so we don't have an algorithm to go ahead. And even if we had more qubits and better qubits, we would not have an algorithm. So we will have a lot of computational resources, but we will not know how to use it. And it will be like, okay, let us compute lots of things, but we have no clue about how to do that. That being said, if we had better computation algorithms, better optimization algorithm, we will have still to face several and serious problems on the computers. But first, we have to know what these problems are, and that can only be done if we have the proper tools. But this is a personal opinion. I don't have any reference on that.
Well, it's the question of the century, right? At the end of the day, I guess there is groups of people pushing the boundaries on everything at the same time, on more qubits, less noisy qubits, more algorithms, different types of algorithms and architectures and topologies. So it might not be one single problem, but all at once. Sorry, Alex, do you have your take on this?
Yeah, I mean, I would say I agree with Adrian. One of the things is that there is the part of algorithm, and there I think there is still research to do to understand how you have to construct this, for example, variational quantum circuit to be efficient. No? And this is, I think, now pretty like hot research topic. Like try to understand what kind of architecture, but all this question that I was also addressing. No? Like imagine you would like to put more qubits, but or more like kind of like parameters in your system, but would it be like more expressive? Because if you would have more like parameters, it's not more expressive, then it's a bad idea to construct such kind of variational quantum circuit. So I think like from this, already from this NISQ device viewpoint, like this noisy intermediate scale device viewpoint, there are many questions that are pretty interesting and that have to be answered to like go to scalability, you know, like to bigger system. So
maybe I would add one more thing that you mentioned on your slides, that is the actual optimization that happens classically. That's a big limitation that we have today, right? Once we add parameters that we have to calculate classically, we can achieve great advantages on the quantum side, but that part, I would argue, needs more work, right?
Yes.
And in addition, I think there is a wrong idea that we have inherited from classical machine learning, and it's the fact that neural networks are very easy to scale. You can, more layers, more neurons. Everything is going, it's like self-contained, and you can make it as big as you want without worrying about nothing else than how much power do you have to train this thing. We are not sure yet about the fact that quantum algorithms behave in the same way. We don't have any evidence on that.
All right, really good answers. We are over time, 10 minutes, but I think it was worth all these questions and answers. So thank you, everyone. As I was saying before, the calendar for next year, we're gonna have a little stop during December so we can enjoy our special Christmas with not many people in the groups. But we will be back in January with randomness. We will talk about quantum random degeneration, and we'll have guest stars and guest speakers for that. In February, we will talk about the first and today's second quantum revolution. And then moving forward, we will talk about cryptography and both quantum and post-quantum cryptography. And we will be introducing more and more companies from the Barcelona and Spanish ecosystem. So really good agenda lined up, both the speakers and the topics. We invite you to join. Once we are able to log back into Meetup, we will start putting all these details. In the meantime, thank you very much for the amazing speakers today, Adrian, Alex, and Gorka. Amazing work, slides, presentation, and great to have it was a pleasure to have you guys with us today. And for the rest, enjoy the rest of November, December, and we will see you in January. Thank you very much, everybody.
Thanks.
Bye. Thanks for
everyone.
Thank you.